Math 4 Honors Arlington High School lesson, or the other way around. Who cares? Today, we're going to be doing another day with AP motion problems. So this is AP motion problems day 2. Specifically, we're going to look at a second set of 4 motion problems that are taken from the Advanced Placement Calculus BC exam. All of these problems only have differential calculus in them. Anything that involved the integral or the process of integration has been removed from the problems. Let's jump right into them. Alright, again, let me apologize for the quality of the problems. A scan of a scan that's then been clipped and cut and pasted into here. It's good enough. An object moving along a curve in the xy plane has a position x, y at time t given, not here, but what we're given are the two velocities, right? dx dt and dy dt. The velocity in the x direction, if you will, and the velocity in the y direction. It tells us also that at time t equals 2, the object is at a position of 4, 5, and the first thing that we're asked to do is something that we're very familiar with. Write the equation of the line tangent to the curve at 4, 5. And again, as we've discussed a few times, we can write this in one of two forms. We can either go Cartesian, in which case we have y minus y1 equals m times x minus x1. Right, we already have x1, it's 4. We already have y1, it's 5. The only question really is what the slope is. The slope of the tangent line will always be dy dt divided by dx dt. All right, and that's going to be specifically at t equals 2. Now they've given us expressions for dx dt and dy dt. The AP, and for my own students, I don't want to see it either. They don't want to see you plug t equals 2 into these two expressions. They simply want to know what the values are. You don't even have to show them these, but let me kind of put them out there. dy dt was negative 2.270. dx dt was negative 0.146, etc. When we do the division, we find that dy dx is 15.604. So I'll write my final equation right up here. Y minus 5 equals 15.604 times x minus 4. Good Cartesian equation. Most students will give that. On the other hand, since we are dealing with parametric motion here, right, we could also give parametric equations. They would look something like this. X would be 4, that comes from its initial value, minus its slope, which is 0.146 times t. Y would be 5 minus 2.270 t, where t goes from negative infinity to positive infinity. And I missed the word parametric. Oh well, I think it'll forgive me. All right, either one, again, I would suspect most people would go with the Cartesian form, but the parametric form is completely acceptable. Letter B, find the speed of the object at t equals 2. Testing a very basic idea, right? Do you understand that the speed is the magnitude of the velocity vector? So first, maybe we write out the velocity vector. We already have its components, negative 0.146 and negative 2.270, right? So the speed is simply the size of that vector, right? So it would be 0.146 squared, 2.270 squared. Ugly answer, but 2.275. Very mechanical, really, both of those problems, right? Form the equation of a tangent line, come up with the object's speed, nothing really tricky. The trickiest parts of this particular problem came with the use of the integration and with the use of what's known as the integral. And if you have no idea what I'm talking about, that's okay. You'll learn it next year, probably, or later on this year in your calculus classes. I'm going to scrub out the text, so please pause anything that you need to. All right, here we go. And it's gone. Next problem. This one's cool. I hope I didn't crowd too much into the sheet. We're going to see what we can do with the limited space. Take a look. A particle starts at point A. Let's really read this together. And the page is cleared. A particle starts at point A on the positive x-axis at t equals 0. Travels along the curve from A to B So I'm going to actually put some direction arrows on here from B to C and from C to D. All right. The coordinates of the particle's position, x and y, are differentiable functions of t, where x prime, the velocity in the x direction, right, is given by this. The velocity in the y direction is given by this expression. Actually, it's not explicitly given. I apologize. At t equals 9, the particle reaches its final position at point D. So in other words, this consists of t equals 9, and this is at t equals 0. All right, I love letter A. At point C, hone in on it, at point C, let's go green. At point C, is dy dt positive? Is dx dt positive? Give a reason for both. I'd like you to pause the video right now and think about this. It's actually relatively easy, but consider it. All right, well, it's pretty easy because the final answer is no to both of them. This is a big fat no, and this is a big fat no. In fact, both of them are negative, right? In order to go from C to D, okay, both x and y must decrease. Thus, that's beautiful, dx dt and dy dt must be less than 0. Another nice way of looking at it, I'm going to actually, let me erase a little bit. I'm going to erase some of this mess so that we can see it a little bit better. Another way to look at it is say, well, look, if I drew the tangent line in there, or maybe it would even be better to call it the tangent vector, that thing clearly has a negative y component and a negative x component, right? The velocity must have negative components on both of them. All right. Let's take a look at letter B. The slope of the curve is undefined at point B. That's about the biggest duh ever, right? That big sharp corner at point B has an undefined slope. At what time t is the particle at point B? So when does it reach point B? Again, pause the video. This is a nice thinking problem. Unlike problem 1, which was very mechanical, each one of the parts of this problem requires some real thinking. So I want you to pause the video right now and think about how we could figure out the time at which the particle has an undefined slope. All right, let's take a look at it. Well, if you don't know what to do anything you can do, right? We know that the slope along this curve is dy dt divided by dx dt. And what we're told is it's undefined at point B. Well, in order for the slope to be undefined, the denominator has to be 0. dx dt has to be 0. So ultimately, what we're doing is we're solving this equation. It's a scary looking equation, isn't it? Now, that being said, this equation actually can be solved algebraically. But this problem, the intent of this problem is to be done with a calculator, all right? So you could go back into function mode and you could solve this graphically. Again, it can be solved algebraically. It is a trig equation, so it has like an infinite number of solutions. But on the interval, on the interval 0 to 9, right? Because we start at t equals 0, we end at t equals 9. The only value of t for which that's true ends up being t equals 3. And again, you can actually substitute it in here and think about this. If I put 3 in here, right, I would get pi over 2, and the cosine would be 0. And as a bonus, although it wouldn't be necessary, if I put 3 in here, I would have the sine of pi, which is also 0. So t equals 3. That's when we're at point B. Let's see. Letter C. The line tangent to the curve at the point x of 8, y of 8, right, has the equation y equals 5/9 x minus 2. So I don't know when that is. I do know it's somewhere between point B and point D, right, because this now we know is at t equals 3, that's at t equals 9, so t equals 8 might be, I don't know, let's say it's right there. T equals 8. And what they've done is they've given me the equation of, if you will, that was like one of the worst tangent lines ever. But they've given me the equation of that tangent line. My apologies. And we need to find the velocity vector and the speed of the particle at this point. Again, this is a wonderful question to think about. So I'd like you to pause the video and maybe take up to 10 minutes to really think about this. Work your way backwards. Ask yourself, what do I need to know for the velocity vector? What do I need to know for the speed? All right? Do not oversimplify it. It's not a really, really simple question. It's not terribly difficult, but it's not really simple. Okay? So take a little bit of time. Pause the video now. All right. Before we look at the correct way to do this, let me show you the incorrect way of doing this. You see, what a lot of people will do is they'll say, hey, I know that the slope is dy dt divided by dx dt. And I know that's 5/9. So I know dy dt is 5 and dx dt is 9, so I already have the velocity vector and I can find the speed. The problem is, it's the wrong answer, right? I don't know what dy dt is, and I don't know what dx dt is, because for all I know, it may be 10/18. It might be 15/27. It might be even something stranger than that, right? I don't know, okay? In fact, I'm fairly certain dy dt is not 5, because I'm fairly certain dy dt is probably negative, right? And so is dx dt. So that's making the problem too easy. All right, now, what I can certainly say, there's no question, is, I can definitely say that m is dy dt over dx dt. And I can certainly say that ratio is 5/9. What I can't say is what either one of them is, until, of course, I realize that they've actually given me the expression for dx dt. So what do? Well, I take x prime and I evaluate it at 8. That's just what I do. I take 8 and I plug it into that horrible-looking formula, but I put it in there. And here's what I find. I find that dx dt is negative 4.5. So then I just set up a ratio, right? Let me use y prime. I'll say y prime, actually I shouldn't say y prime of t. I should say y prime of 8. Uh-oh.
Emily Bayram, if you're in the building, please report to the central house. Emily Bayram, if you're in the building, please report to the central house.
This is now the equation that I'm working with. Right? Y prime of 8 divided by x prime of 8 is 5/9. Little cross multiplying or proportional reasoning or what have you. 9 times y prime of 8 would be equal to whatever that ugliness is. I didn't even work it out. I don't really want to do that. Negative, I think it's negative 22.5. Please tell me that's right. Yeah, I think that's right. But y prime of 8 ends up being negative 2.5. Think about that. Negative 2.5 divided by negative 4.5 is the same as 5 divided by 9. So now we actually have the velocity vector. The velocity vector is negative 4.5 comma negative 2.5. Again, it gives me the ratio of 5/9. And the speed, of course, is its magnitude, and I'm not going to work all that out for you. You know how to find the speed by using the Pythagorean theorem, but it would be 5.148. That is an AP problem, right? Forces you to really understand what's going on. Really understand. Okay, I'm going to clear all of this out, so please copy down whatever you need to. Okay, here we go. I liked that one. And if that one was good, this one's great. The figure above shows the path traveled by a roller coaster car over the time interval 0 to 18 seconds. The position of the car at time t seconds can be modeled parametrically by those two position formulas. And then they were so nice, they gave us the derivatives. They just said, we'll do it for you. So they came up with the derivatives, all right? We could do that ourselves. Now, I really want to keep in mind that this is the actual path that the roller coaster traveled. In other words, that's x, that's y, t is not showing up. First question's not too bad. It says, find the slope of the path at time t equals 2. Show the computations that lead to your answer. Pause the video now. This isn't too tough. It's a little bit messy, but it's not too tough. And figure out the slope of the path, okay? All right, let's go through it. Slope of the path is always dy dx, but that's dy dt divided by dx dt. And again, we have those. All I have to do is take t equals 2, substitute them into these two formulas, right? If you really want, you could say that's y prime of 2 divided by x prime of 2. Good notation use there. Let me figure out what those values are. I certainly don't have them memorized. It's 14.9512, etc., divided by 8.335, etc. So the slope of the path is an ugly 1.794. 3 decimal place accuracy, AP standard. Let's see. Find the acceleration vector of the car at the time when the car's horizontal position is 140. Ooh, I like this one. Pause the video and really, really think about this, okay? All right. Well, normally, especially when we have an expression or have expressions for the velocity, right? The velocity in the x, the velocity in the y. When we have these two, finding the acceleration vector tends to be a snap, especially like in this problem when we've got our calculators, because I'll just do a little numerical derivative. I'll plug in the value of t and, oh, that's a problem. I don't know the value of t. I know the value of x, right? So I'm saying, I don't know where it is. It's about here, right? Here's 140, right? I want to know right there. So the first thing I really need is I need the time, right? I need to solve when the horizontal position, take a look, this is x of t, I need to figure out when that's equal to 140. And I need to be able to solve this graphically. All right? And again, the thing that's a little bit confusing about that is that you really need to go back into function mode on your calculator. And you need to go back to y's and x's, keeping in mind that when you solve for x, you're actually solving for time. That's a little confusing. But again, that's not really the point of the problem. You should easily be able to say, all right, I set that, I got to figure this out, looking for it. I set that up, I solve for it, and I'll find 13.647, the units there are seconds. So that's when I hit it, but now it's easy because the acceleration vector is always the derivative of the velocity vector. And again, I love the notation here. We're just going to put in at 13.647. You don't need to show how you find that derivative. All you have to do is establish the fact that the acceleration is the derivative of the velocity vector. Then we're going to just simply use the numerical derivative command on our calculator to find the derivative of both of those. People are beating down my door. And that ends up being ugly again, negative 3.529 and 1.226. So again, we're going to do this by using a numerical derivative. You could do it by hand, but it would take quite a long time, more time than you have. If your teacher hasn't told you, and I don't think I really have, you only have on average 15 minutes for each one of these free response problems. And we're not done with this yet. So you don't want to spend 5 or 10 minutes doing the product law and dealing with trig derivatives on this when it should take you only about 2 minutes to find the derivative numerically. All right? So I'm going to be clearing this out in a moment. Copy down anything you need to. All right, we're doing fine on time. All right, I recopied the graph and the original setup so that we could do Part C. Part C asks us to find the time at which the car is at its maximum height and find the speed in meters per second of the car at this time. So let's highlight that, shall we? Here it is. That's our maximum height. And we need to find that. Now, what's cool about that is it's really the first point in time, right? It's the first point in time when dy dx, I think we'll stay in red, is equal to 0. But since dy dx is y prime divided by x prime, it's really the first time when y prime of t is equal to 0. So I need to solve this equation, 20 minus t times sine of t plus cosine of t minus 1. I want you to keep in mind that that negative 1 is not paired with the t. It's paired with the cosine t, right? So it's not that, right? I'm going to, again, solve graphically. Right? Go back to my function mode, plug that in, use the 0 command, etc., etc. And what we find is that that will occur for the first time at 3.024. Actually, it occurs for the first time at t equals 0, but besides that, it occurs at 3.024. Great. We need to find the speed of the car. Well, we know speed is the absolute value of the velocity vector, or the length of the velocity vector. So what I'm going to do is I'm going to figure out the velocity vector at t equals 3.024 by simply substituting this into these two expressions, right? And that is going to result in something, 6.028, 0. One of the things that's cool, and side note, I hope that we're not surprised by that, wasn't that sort of the point of this, yes, is that then the speed just becomes the x component of the velocity. Right? It really just ends up being that. You can go through the speed formula if you like, but you're going to square 6.028 and then take its square root. You're going to get 6.028. Now, it's important to note that if, let's say, that x velocity was negative, the speed would still be positive. Excuse me. All right, I'm going to clear that out. Let's go on. Let's look at the last problem. Okay, a particle has a position x comma y as a function of time. The position of the particle at t equals 1 is 2 comma 6, and the velocity vector is given by that expression. So it's actually important to note right from the get-go that what they're giving us here is v of t, okay, the velocity vector. They want the acceleration vector at time t equals 3. Go for it. Easy enough. All right, not much work we even have to show for this. I'm not sure why I gave this much space. The acceleration vector is the derivative of the velocity vector, specifically at t equals 3. So we'll do that with a numerical derivative again. Numerical derivative. We're not going to show the numerical derivative command. We're just going to show this. All we have to do. But it ends up being quite small, actually. 0.074 and negative 0.074. Kind of interesting. We've got like a sort of a 45-degree angle going on, or if you really want, a negative 45-degree angle. That's it. Letter C, though. Skipped over letter B. It involved integration. Letter C asks, for what time t greater than 0 does the line tangent to the path have a slope of 8? This is a problem worth its weight. Okay? So I want you to pause the video, and I want you to figure this out. All right, let's do it. You can solve much of this algebraically, but again, we have our calculator, so we could also solve it numerically. Right? They're telling me that the slope is 8. And what I know is I know that that's y prime of t divided by x prime of t. So that's 2 plus 1 over t squared and 1 minus 1 over t squared. So effectively, I'm solving this equation. Now again, you can actually solve this almost entirely algebraically, and when I wrote out solutions to it, that's what I did. But you could also solve it graphically. And I would imagine many students would probably do that because we've been doing a lot of it in these problems. Either way, what you eventually get is you get t is equal to 1.225. Whether you solve it graphically or algebraically, that's your final answer. All right, let's look at problem D. I like this one too. The particle approaches a line as t heads towards infinity. Find the slope of this line. Show the work that leads to your conclusion. So that's kind of cool. I really want you to sort of understand what they're getting at here. If I could somehow graph the position of this particle, x versus y, as a function of time, I don't know what it looks like. But eventually what they're saying is eventually that thing starts to look linear. It has an asymptote, a linear asymptote, and what we want is the slope of that line. I'd like you to pause the video and take a shot at this. I think you can figure it out, okay? Let's take a look. Well, for any time t, the slope is going to be y prime of t divided by x prime of t. And that is going to be 2 plus 1 over t squared divided by 1 minus 1 over t squared. Now, generally speaking, right, that changes as t changes. But we can look at the limit of this as t goes to infinity. Now, I always advise my students to understand what's changing and what isn't. And what's changing are these terms 1 over t squared. As t goes to infinity, 1 over t squared goes to 0. So this goes to 0, and this goes to 0. So we end up having 2 plus 0 divided by, whoops, I don't know where that thing came from, divided by 1 minus 0. So the slope eventually heads to 2. So it approaches a line with a slope of 2. I don't know what its y-intercept is, but it approaches a slope with a line of 2, or a line with a slope of 2. A slope with a line of 2, that's awesome. All right, I'm going to clear this out. All right, it's gone. Okay, that was our second day on two-dimensional AP problems. Again, we left a lot out because there's a big tool you haven't learned yet in calculus called the integral and integration. But still, there's a lot that my students can do at this point with two-dimensional motion, specifically thinking a lot about velocity, acceleration, and speed. Ironically, it's a little bit harder for you to think about position, especially if you begin with velocity. Then position is very hard to think about because for that you really need the integral. All right, we'll stop there. Let me remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.